All right, so last time we were talking, we're going to continue with thinking about the rotating momentum equations. And I suspect everybody's forgotten what we did last time, so we will quickly review since it's been almost over a week. And the most important thing is that I have pushed the homework date back a little bit because we're not going to have enough time to talk about Ekman before you do it. So I pushed the homework and the plans back a little, but I did not push the paper date back. I just moved them closer to give you a little more time to think about it. So as you're doing your homework, simultaneously be thinking about your plans. They'll come together. The basic gist of this paper is to think about Ekman transport. And so we're going to talk today, if we get to it, and definitely on Tuesday, about some consequences of the Ekman transport. And so something relating to that is what you're going to do the second paper on. Thanks for getting all the papers in on time. That was great. And for getting all the reviews in on time. I mean, the revisions are all in or up. Most of them are anyway. So that's great. And I'll get those back to you shortly. Are there any questions about that process? Yeah.
Do you know on overlay, way to compare versions? That's what
I found a web page that you can download and run LaTeX diff outside of Overleaf and then reload it back up in, but no, not within Overleaf, I don't think. Do you know how to run LaTeX diff?
So you can do a compare changes in Overleaf, but you can't print that to a PDF.
Right, you can just do it in like a text file, right?
Yeah.
Right.
Is that sufficient?
Yeah, that's fine.
Okay.
I don't mind reading LaTeX. That seems just fine. But there is a program called LaTeX diff, which you can run, and it makes a beautiful kind of track changes PDF, and it even does equations. So it's worth learning how to use it if you're interested in learning more about LaTeX. And it's whatever. It's a little finicky to get it started, but once it's going, it's beautiful.
I think there's a package you can install on Overleaf that is part of
Maybe lets it run.
Yeah, I tried to mess with it yesterday, but it was too late.
Okay.
Okay.
But
That package still won't print to a PDF though.
Sorry.
That package still won't print to a
Yeah,
PDF.
yeah. But it's okay. It's okay. And there were some other problems with getting track changes. So Microsoft Word doesn't want to do track changes the right way. So if you print the track changes version of Microsoft Word with the comments on the side, and then you can upload that as a PDF. So whatever. This is part of the kinks we're working on. But does the system make sense to you, how everything worked? And do you feel like the reviews you got back were actually helpful? I thought everybody did a good job of coming up with good reviews, so I thought that was a big strength. So we'll see. So next time will be better, even. All right. Okay, so last time we started talking about the equations of motion in a rotating frame. And so remember we had this little diagram that was, there's a rotation axis and there are two coordinate systems, one that's whipping around and then one that's inertial. And we found that there are two forces that come out of that transformation, so that the acceleration term in the inertial frame, you have to also add, so this is the one that Newton's second law applies to, because you have to be in an inertial frame to use Newton's second law. So you have to add these two other terms, the Coriolis term and the centrifugal force, onto that to get the acceleration in the rotating frame. So on the Earth, for what kind of motion do we worry about these two forces?
Rotating.
Things that are, so the Earth is always rotating, but so how do we think about when rotation is going to be important? Or maybe put it another way, how big is 2 omega? Omega is what? It's the angular velocity of the rotation. So it's 2 pi radians per 24 hours on the Earth. So this is 4 pi over 24 hours times a velocity. This is a velocity per unit time. So how do I make this term bigger than that term? Accelerations have to be really slow compared to the Earth's rotation, or really fast compared to the Earth's rotation? if it takes a long time to change the velocity, this term will be whatever size it is over a very, very big thing. So this will be a small term in comparison to this. If it goes really, really fast accelerations like that, this term is much, much bigger than that. We don't have to worry about the Coriolis force when we drop something under gravity in air, right? Does that make sense to everybody? We're going to get a little more formal in a little bit. We're going to take the ratio of this term to this term and think of it as a dimensionless constant called the Rossby number. So that's one piece we're going to go. Okay, and then there's the centrifugal force. And I said we don't have to worry about the centrifugal force. I'm going to show you graphically on the next couple slides why we don't. Okay? And so this was our fluid momentum equation for the inertial frame. This is Newton's second law with the pressure gradient force and the gravity. Remember we had hydrostatic balance between those two? So if I take the centrifugal force and absorb it into a part of the gravity, which we're going to see why I can do that in a second, and I take the Coriolis force and just add it in, this is my equation in the rotating frame. Okay? So there's regular old material derivative of velocity, there's Coriolis, pressure gradient force, the geopotential gradient, which has both gravity and the centrifugal force in it, and then any other forces that are being applied, like friction or something like that. Okay? All right. So, I got this wrong last time, so we're definitely going to dwell on this for a moment. So I said that if I let this hang, it doesn't point to the center of the Earth. I actually said it points a little bit more to the pole, but that was wrong. It points a little bit past the center of the Earth because gravity would point to the center of the Earth, center mass of the Earth. The centrifugal force would point outward from the rotation axis. And if you add those two together, you get something that goes like that. That is actually the local vertical. The local vertical is not in the direction of gravity. It's in the direction of the combination of gravity and the centrifugal force. And I can also tell you pretty confidently that this floor is perpendicular not to gravity, but to that net. How do I know that? It's probably not perpendicular to anything exactly, but what would happen if it wasn't? If I put a ball on the floor, what would it do? It would move. If either gravity or the centrifugal force had a component in the direction of the floor, it would start moving. So what we mean by the local vertical is actually the combination of those two. So it's the local vertical is in the direction of the gradient of the geopotential, which is the combination of the gravitational potential and the centrifugal potential, which is a complicated way of saying it, but that's what flat means perpendicular to that, vertical means in that direction. But what the great advantage is that we no longer have to worry about the centrifugal force. We're just going to stick it in there and then it's gone. It goes together with gravity. We don't have to think about it very much. This also works in a rotating tank. So here's a cross section through a tank of water that's rotating. When you do that, the surface will come up into a parabola, and that parabola will be just enough so that the pressure gradient force will cancel the centrifugal force. But the local vertical, that thing perpendicular to that surface, will be the combination of centrifugal plus gravity, just like the surface of the Earth. Does that make sense to everybody? So you have these funny combinations of the two. But in this tank, again, we could do experiments in a tank, and because the surface comes up like that and cancels out the centrifugal force, the only extra force of motion here would be the Coriolis force, just like on the surface of the Earth. The only force we have to worry about is the Coriolis force because the centrifugal force gets absorbed inside the gravity term. Okay. before I move on, are there any questions about that? It's kind of just gobbledygook. The equations that I've shown you actually have the whole story there if you want to go back and think about it more. But the practical perspective is we don't have to worry about the centrifugal force being in our equations of motion. It's already absorbed inside of gravity. And that's true in the rotating tank, and that's true on the surface of the Earth. Does that make sense? Okay. There's one more simplification to the equations of motion. So, how many of you have seen spherical coordinates written out? Yeah, so sometimes it's an E and M. So, we're not going to dwell on spherical coordinates, even though we could. It makes everything much more complicated. For all the purposes we're going to talk about, virtually all, we can do a tangent plane approximation and just worry about a tangent plane. And what that means is that our gradient just is ddx, ddy, ddz relative to this plane. So ddz is in the local vertical, ddx is traditionally in the east direction, ddy is traditionally in the north direction, and it basically makes our equations of motion a lot simpler. So if we do that, it's called, and we neglect the fact that the rotation axis is like, all right, if we're on the pole, we're rotating really fast in the vertical, right? Like here. On the equator, we're rotating like this. Or maybe I should have done that backwards. At the pole, we're rotating about our local vertical axis. At the equator, we're rotating, the vertical axis is like this, and we're like this. So we're rotating around like this. Our local vertical is actually perpendicular to the rotation axis. So this local vertical is perpendicular. Well, it turns out when you make this F-plane simplification, the only part that survives is not the full angular acceleration, the 2 omega that's in the direction of the axis of rotation. It's the part that's just the local vertical part, which we call F. Okay? So at the pole, we get all the 2 omega back, but it comes back, so the F naught there would just be equal to 2 omega in magnitude. Here it would be 2 omega times some trigonometric factor. Here it would be 0. Okay? Does that make sense to people a little? Yeah.
Sorry, it would be, when we're at the poles, it would be twice at the magnitude?
Sorry, oh yeah, sorry, there's a 2 that drifts around. It's 2 omega is F naught, and it's 2 omega times the sine of the latitude. So at the pole, where the latitude is 90, F naught is just equal to 2 omega. At the equator, where the latitude is 0, F naught is 0. Okay, and this is sort of a convenience thing that makes it.
The 2 from?
The 2 comes from the 2 hiding on the Coriolis force. Why is there a 2? Because we got an omega cross VR 2 times. We got one when we went from position to velocity, and then we got another one when we went from velocity to acceleration, and they add together in this term. Okay? We can go back and look at it if you want to see it. So we get 1 when we go from, so we get 1 when we compare the inertial velocity to the rotating velocity. We get 1 omega cross r. And then if we take the time derivative of this equation, we get a ddt of omega cross r, which gives us 1 omega cross vr, and we get another omega cross vr because we have the omega cross vr from that original formula. So we add them together and it ends up having a 2 out front. There's 1. This 2 is hard to keep track of, and it means that the inertial period is different than a day, which we'll come up with another way to think about when we get to inertial oscillations. But it's essentially coming out from this algebra. Okay? Okay. So this is actually a little bit of too much of a simplification. We'd like to preserve some aspect of the difference between the equator and the pole. So F naught is a constant with a constant latitude that's the center of this plane. It's actually a little more accurate to do a Taylor series and expand this sign out to have a constant plus a linear change in latitude. And that's called the beta plane. And so it's still a tangent plane approximation. It's just a higher order approximation to the tangent plane. And that gives us F being this constant F naught plus something that's linearly proportional to Y. And so in the northern hemisphere, F is greater than 0, and beta is also greater than 0. In the southern hemisphere, F is less than 0, but beta is still greater than 0. Beta is talking about when you head north, you're always increasing your local component of rotation in the same sense as the way the North Pole is rotating. Does that make sense? So this is a little tricky. We'll come back to this one. This one is really deeply entwined with why the Gulf Stream is on the west side of the ocean instead of the east side of the ocean. We're going to spend a lot of time thinking about that. But for now, it's just we take this tangent plane and we do a Taylor series on this expansion, and then we just keep the first two terms. Okay? If we were right at the equator, F0 would be 0, and we could have just the beta y part. If we were right on the pole, beta y would be 0, and F would just be a constant. Does that make sense to everybody? Sort of? Okay. All right, so all that being said, we can now write the equation of motion in the form that we need for everything. Now we've got a full set of equations. We've got it's all closed for all the variables. And so from now on, we don't want to talk about where the equations come from, except to remind ourselves, we want to talk about what the solutions look like. Okay, so we're not going to solve these equations like this, or we're not going to. The ECHO model actually solves something quite close to this with just a few approximations. But it is different than we are in that it does not blink at nonlinearities in the equation of motion. Remember, the big DDT hides a nonlinear v dot grad of whatever is being vected in it. So this is a nonlinear equation, 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 this is a doubly nonlinear equation because there's that one and also that one. So we don't want to solve those directly by hand. So instead, we're going to look for particular classic solutions to these equations, which in a particular regime, we can think of other balances that are worth thinking about. And we already thought about one. What was that balance? Very good. So we balanced this term against this term, and we said that was the hydrostatic balance. And it was hydrostatic because we threw away all the terms that depended on velocity, so it was not moving water. And then we didn't worry about friction in that case, and we just balanced those two. So that was the first balance. But we're going to think about one called the geostrophic balance, which is this one and this one, the Ekman balance, which is this one and this one. We can talk about the cyclogeostrophic balance, which is this one, and this one. So, and so on and so forth. All of those neatly avoiding the nonlinear term. So the balances we're going to study are the ones that are linear, which makes it easier to think about. But the ECHO model is fully nonlinear. So in comparing the solutions coming out of ECHO to these balances, we can learn about the effects of nonlinearity because there'll be deviations from our simpler theory that we can do with pencil and paper. Does that make sense to everybody? Okay. All right. So now let's start talking about how do I get rid of all these terms? How do we get rid of them in the hydrostatic balance? We just said V was 0. Forget the motion of, if we set V to 0, then this one goes away and this one goes away because they both depend on V, and we were just neglecting friction. We said that one balances that one. But we could be a little more subtle. We could say maybe it's not exactly 0. What if things are just really, really big versus other things? So, which is called scaling the equations of motion. This is one of the most powerful ideas in fluid dynamics, that you figure out how big is that term going to be? 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 And if 2 of them are bigger than all the rest, then they pretty much have to equal each other because the rest are all just sort of small background noise. Okay? How do I figure out how big this term is? Suppose I know I'm studying a current and the current goes 1 meter a second.
We can assume that dV dt is basically 0 since it's all the same current for exactly the same speed.
True. So if we had a constant flow, then the acceleration might be 0. The dV partial dt might be 0. But even if it was accelerating a little, we could still estimate it. We could say, suppose it's changing, 10% over 10 years. Then we would say 10% of V over 10 years. And then we'd have a scale estimate for that term. For the Coriolis term, things are actually a little easier, because if you go and you say, I measure my velocity as 1 meter a second, I know what 2 omega is. It's 2 pi, or it's 4 pi per 24 hours. And so I know what that is. So I know how big this term is. Here, the accelerations, I kind of have to put in more information. The pressure gradient is really hard because it tends to balance whatever else is going on in the equation. You could go and measure the pressures, and you could do that particularly with sea surface height. We'll see how to think about this term, but that's hard. How big is this one? This is the geopotential, or it's mostly gravity. So the acceleration due to gravity is what?
About
9.81 meters per second squared, so we know how big that one is. And then this one, if it's friction or something like that, we would have a viscosity. We'd be able to kind of guess the scale. But today we're really interested in this guy versus this guy. So this one, remember, has a rate of change part plus an advection part. This one, you could say it's steady or it's nearly steady. That's easy to figure out the size. This one is harder because it's nonlinear. It depends on gradients in a complicated way. So we want to get rid of this term, essentially. So we're going to think of a limit where that goes away. So what if I just take the ratio of this piece and this guy? So V dot grad V over 2 omega cross V. And assuming that the directions were all not some crazy pathological direction where it went to 0 in the denominator or something like that we get worried about, we could say that this is basically the size as the velocity times the velocity over some length scale. Does everybody see that? This is so this is like the size of whatever our typical velocity, say 1 meter a second. This gradient of the velocity is going to be velocity divided by whatever length scale it's changing over. So this would be velocity squared over length. And then down here we know what 2 omega is, and we have another velocity. So if I just approximate those, this velocity would cancel one of the ones upstairs. There'd just be a velocity scale. And here I'm using capital letters to indicate the magnitude, not necessarily with any direction on them. It's just kind of like ballpark. How big is this? So this is 1 meter a second, and it's a particular direction. It's a vector. Let's just use 1 meter a second as the scale for that velocity. And then 2 omega comes from that, and there's the length scale that comes from the gradient. This is called the advective Rossby number. This is one of the most important things in rotating fluid dynamics to think about. When is this term going to be big?
The velocity is big or length scale is small.
Good. Or the rotation rate is really, really slow, is another way to think of it, right? On the Earth, we know what the rotation rate is. And then we're thinking of really this U over L in comparison to that rotation rate. So if U is 1 meter a second, then we could ask, at what L do we have to start worrying about this term? Because we know what this guy is. If this thing is, so we could set that up to be equal to order 1 and solve through that equation. Or we could say, suppose the current I'm interested in is 100 kilometers wide. Then I could say, well, at what velocity would it need to measure, would it need to go before this term becomes sizable? And remember, since it's the ratio of this term to this term, if this thing is small, if we go out in the real world and check it, and it turns out to be small, it means that this term is bigger than the nonlinear part of this term. And so we can just throw away the nonlinear part of that term. Okay, so let's crank an example. What's the current that we want to talk about?
Gulf Stream.
All right, Gulf Stream goes about 1 meter a second. U is about 1 meter per second. The width of the Gulf Stream is about 100 kilometers, which is 10 to the 5th meters. The Coriolis 2 omega is 4 pi over 24 hours, which is 12 over 86,400 seconds. Everybody with me? And now we have to actually do some math, figure out what that number is. And it's about 1 times 10 to the minus 4 per second. Ish. Right, this is like 10 to the 5. That's like 10. 10 over 10 to the 5 is about 1 times 10 to the minus 4. Close enough. Okay, so what's U over 2 omega L? That's going to be 1 meter per second over 1 times 10 to the minus 4 per second times 10 to the 5 meters. And the meters cancel out, and the per seconds cancel out, so we have a dimensionless number. So it doesn't matter whether we measure it in feet per second, furlongs per fortnight, whatever. We're going to get the same answer, right? And what is it? 10 to the minus 4 times 10 to the 5, 0.1. So the Rossby number of the Gulf Stream, which is one of the more intense large-scale currents, is still only 0.1, which means that that nonlinear term is only 1/10 as important as this term. Even the Gulf Stream, we can neglect to leading order the nonlinearity. Okay? We could have done exactly the same game with the DDT part, and then you have a temporal Rossby number, and that would basically say, so we get the V out of this, we get a time scale out of that, we get the V, the V's cancel, and we basically get 1 over 2 omega t. So what does that say? How do I think about this one? Yeah?
It's like at what time scale is this effect going to be significant?
Exactly. So if I have really, really big time, this is going to be a really small number. If I have a really, really small time, this is going to be a big number. So this is saying, another way to think of this is, how important are my accelerations to the rotation of the Earth? So if my accelerations are fast, this will be a big number. The time scale will be small. If my accelerations are slow, this will be a small number. And then I can neglect the DDT versus the Coriolis force. Does that make sense? So how can I think about this? How big is 2 omega? 12 over a day. So 12 over a day, so how many days do I have to be going to have this how big does T have to be to make this be a negligible term? Yeah, so this one is about 2 hours. So this is 1 over 2 hours essentially. So this is saying when my time is much bigger than 1 over 2 hours, multiple hours, days. So as soon as we get to days, this starts being a small contribution. Because basically your relative acceleration of going around and around the Earth is much bigger than the local accelerations you might experience as soon as your time scale is slower than days. Right? That's what we talked about intuitively. This is the number that measures it. Also, this one is dimensionless the same way, so it doesn't matter whether we measure in hours or seconds or years or whatever. Yeah?
Just wondering, when you chose the scale, when you're looking at the cross-current scale versus the long-current scale, is that because you're assuming that it's going to result in an even smaller Rossby number, that it's not worth considering?
Yeah, well, we could have been much more careful, and we could have said, well, which component of this is going to be important, and let's think about this as a vector equation, and then we could have been much more careful and come up with a Rossby number for the cross-stream variation and a Rossby number for the along-stream variation. This just said, just forget about all that stuff, and let's just think about it as a length scale and a velocity scale. Because I could have said, you're right, I could have said the velocity, how long is the Gulf Stream, which would have been more like 10,000 kilometers rather than 100 kilometers.
But then the Rossby number is even smaller.
The Rossby number would have been even smaller. This is potentially the bigger contributor, and so that's the one that we calculated, and it still was small. But you're right, we could have gone more carefully through in both the U equation and the V equation to ask how big the terms are with each of them. And that's not always the case that it would end up being the same in both equations. Okay, so this is the idea of the Rossby number. Okay, so we want to think about our first solution in the limit of small Rossby number with no stratification. This is called the Taylor-Proudman theorem. This is what typical flows do. So what typical flows result from the Coriolis force when nothing else is going on? That's what we're interested in. And so we're going to consider small Rossby, which we could say that that's either dominant rotation or small acceleration. Either way, you can think of it. Okay? Oh, let's go back to our tank. Remember, this is the tank, the rotating tank case. And remember, when it wasn't rotating, we had this kind of a blob of fluid. But when it's rotating, it does something special. It forms these curtains that kind of move around without tilting over. They just stretch out. So that's what the kind of motion we're keeping in mind. Okay? All right. So in the limit of small Rossby number, here's our equation of motion. And I just threw away the big d dt because small Rossby. That's what we just said, was that term is negligibly small if it's small Rossby. Okay, let's throw away friction too. And then this guy is inside of a gradient. Oh, and we're also going to assume constant density. So I can bring the density inside of that gradient. I can combine this gradient together with that gradient. So I've got this thing. This is the pressure plus the pressure per unit density plus the geopotential. It's a big scalar. Here's the gradient of it. It's supposed to balance the Coriolis. Okay? Does everybody see the manipulations I did to get there anyway? What if I could say this was negligibly small, but I could even be more sophisticated and say this whole thing is a gradient. So I can take the curl of this whole equation. So what's the curl of a gradient of anything? 0. So if I take the curl of this equation, I get this equation. Is that everybody on board with that? So this says something funny about the Coriolis term. It says that the Coriolis term doesn't have any curl, which is hard to think about. But let's expand that out a little more. Okay, that equals 0, so the back cab rule, which is like the triple product of this. Has everybody seen this kind of manipulation before? Where I take, so there are two products in here, so I do the B times A dotted into C plus C times A dotted, and I expand that out. This is a calculus identity. This is like the product rule, essentially, but for cross products. So, but This, I claim, this crazy thing, is exactly equal to that. Does everybody believe me on that anyway? Okay. So, let's look at these terms one at a time. So this is V dotted into the gradient of 2 omega. 2 omega is the acceleration rate of the frame, so it has no gradient. So that's 0. Okay, do you have a question, Solomon?
Sorry, could you repeat the name of this identity? I need to look it up later.
Oh, yeah, so sometimes it's called the back cab rule. B-A-C-C-A-B. But it's really the triple product identity for the curl. Because it's 3 things and it's using a curl on the outside. If you write the components out from this, a good thing to do actually is to go through and write out all 3 components of this side, all 3 components of that side, and convince yourself that it always has to be equal. It does. It's just like doing all of the worrying about all the cross products, all the orientations, all that stuff. Okay? All right, so this one, because there's no gradient of the rotation axis is the same wherever we look. This one is 0. 2 omega dot grad V. We better worry about that one. That one isn't, there's no reason why that should be 0, so we're gonna have to hold on to that guy. 2 omega divergence of V. Well, we already know our fluids are normally incompressible, so let's go in the incompressible fluid limit and kill that one. So that guy is 0. V times the divergence of 2 omega. 2 omega doesn't vary either in the gradient or in the divergence, so this one is also 0. Okay? So that means that the only term that survives, if we're incompressible, is this guy. So this complicated looking thing becomes this other complicated looking thing. But this complicated looking thing isn't as complicated as all that. We can move the minus sign over and just think about this. So 2 omega, what direction is 2 omega in? It's up. It's in the rotation axis. So 2 omega dotted into the gradient. So that means the gradient in the direction of the rotation axis. Okay? Everybody's on board with what that means? The gradient in the direction of the rotation axis of the velocity is 0. So that means that if this is the rotation axis, whatever the velocity is at any point, it's the same at every point along that axis. It does not spiral as you go down. It does not go fast at the bottom and the other way at the top. It is the same. The vector components everywhere along that rotation axis are the same. That's the Taylor-Proudman theorem. So rotation stiffens the flow in the direction of the rotation axis. So let's go back to our movie. Can I make it go faster? So which direction is the rotation axis here? It's out, spinning this way. Look, what happens is that it spreads out, but it spreads out like this, like columns or curtains. They don't tilt over, they don't twist, they don't rotate. The velocity at the top and the velocity at the bottom, looking from the side, you can see that they're the same to a good approximation. That is the Taylor-Proudman theorem. So there is no shear, no change in velocity in the direction of the rotation axis. And it just keeps on working. When we zoom in, we can see that there is a little bit of wobbling around that, but it comes back. So there's an oscillation that's growing around it, but it doesn't permanently tilt over and shear out. So that makes the flow really, really weird. I mean, like this is the weird thing about rotating fluids, that they do this. So in the absence, so what were the assumptions we had to make to get there? Let's go back. We had incompressible fluid, small Rossby number, constant density, no friction to get here. Okay? That's when we get these columnar motion. Okay, now what we're going to think about is, what if we let the density vary? Or what if we don't have small Rossby number? Or what if we do have friction? Or what if we were compressible? We'll start relaxing those, and then we'll get different balances. But this is the fundamental one. This is the one that's the way rotating fluids behave in the most simplified setting. Okay? Everybody seems to be sort of okay with that? Okay. So what do the Taylor columns look like in that tank? They look like this. They're little columns in the direction of the rotation axis. Okay? And they wouldn't tip over, and they won't spin. They could spin around themselves, but they can't have any variation in velocity from the top to the bottom. Vector variation. So even components can't change. Okay? So the ink blobs are columnar. What about on the Earth? If this were the dominant dynamics on the Earth, on the ocean we'd have little columns, and they would all align themselves with the rotation axis of the planet, and then they would just slide around. This doesn't work very well on Earth. Why not? What do we already know about that would violate our assumptions in the Taylor-Proudman theorem? The Rossby number is small but not zero, so there's some nonlinearity. Yeah, that's part of it. Yeah.
It's not really incompressible.
It's not really incompressible. This would definitely not be true in the atmosphere because the atmosphere is compressible. But we also know about the thermocline and the pictocline and the whatever, so we know the density is not constant. So it turns out that stratification and rotation kind of compete with each other, in that rotation likes to make things stiff in the vertical, and stratification likes to lubricate the layers so that they slide past each other. So they're kind of in competition with each other. We'll gain a sense of what that is over time, but it's really the stratification of the oceans that makes this not a very good approximation. But there is a planet in our solar system which does look an awful lot like this. So Jupiter has relatively tall columns that we think go down into the cloud layer, and you can see them at the pole. Look at how, so this is from Juno, which until 9 months ago, we'd never seen what the pole of Jupiter looked like. But it has these little vortices, and they're all aligned with the rotation axis. And then when you zoom in into a movie, you can see there are these little vortices all along here. We don't really know how tall they are, but they should be relatively aligned with the rotation axis. And some simulations, making assumptions about how the clouds work, actually make tall columns that go like this rather than the other way. And the red spot, that one, seems to be doing something different. So that is an interesting other question as to why the red spot's different. Okay? So far we haven't made a whole lot of predictions about things that are ocean specific. This Taylor-Proudman theorem should work in any rapidly rotating fluid, regardless of whether it's earthbound or otherwise. Okay. So the main exceptions we're going to worry about are friction, where we're going to get the Ekman transport, time dependence, where we're going to see inertial oscillations, we're going to talk about that in just a second, and density variations, where we're going to see geostrophic shear. Okay, so this is basically the track we're on for the next 2 weeks or so, is to start getting to know what each of these balances are. Taylor-Proudman will be our 0th balance with nothing interesting going on, Then we're going to add a little friction, and we're going to find a different balance. We're going to add a little time dependence. We're going to find a different balance. We're going to add a little density variation. We're going to find a different balance. We're going to understand how those work. Paper 2 is on these two. Paper 3 is on this guy. Okay? That makes sense to everybody? We actually did that in the full 3D 2 omega case. We could have done the same thing on the F plane, this tangent plane approximation, and then it would have just said that F dotted into gradient of U is 0, which means basically since F in our tangent plane we're only interested in the vertical component of F, that means there'd be no change of U, V, or W in the vertical. So this looks a lot like that rotating tank problem. This is what we're going to think about, is what would produce some du dz kind of motions. Okay? All right. So the next piece I want to talk about very quickly are inertial oscillations, which is what if we keep a little bit of just the ddt, the time derivative part in, but not the nonlinear part, just the partial derivative with respect to time. It's those little wobbles right there are inertial oscillations, and we can essentially, we have the equations to show how that works pretty quickly. So if we take our full equation and we make our approximation to throw this side away if we want, so no pressure gradient forces, the same way we talked about as we were thinking about Taylor-Proudman, and we throw away the advective Rossby number but not the temporal Rossby number, we get a partial derivative of time. We get a Coriolis force. So this is one of the two terms inside of there. This is that term. And then we're neglecting all of the other ones for now. Well, they're going to come. All right. We're not really, let me make this clear. We're not actually neglecting all the other terms. We're just kind of looking for deviations. So you know how those little wobbles were on top of a Taylor-Proudman current? The Taylor-Proudman current would have experienced all these other guys that we worried about. Remember we did that trick of taking the curl to bury them? They're still there if we wanted, but we're thinking about deviations away from that. So if you like, there's a current and we're going to perturb that current away from its balance and see what it does. And it's going to give us a little wobble like those curtains were doing. Okay, so for the perturbation velocity, then, if you want to think of it that way, it would have this equation. Okay, so this is a fun little cross product example. Well, I'm going to write it up over here. So this has, if we're thinking of the rotating tank case, which is easy enough, then this has a horizontal in one direction, a horizontal in the other direction component. There's some small vertical velocities, but let's just think of that direction. So there's a one direction horizontal velocity, there's the other direction horizontal velocity. Because of the cross product, these guys get scrambled. So the Coriolis force acting in the u direction depends on the v velocity. And the Coriolis force acting in the v direction depends on the u velocity. And this goes back to the, I didn't talk about, but I will talk about now. So if we're on the surface of the Earth, which way does the Coriolis force push us? You guys heard this in any other classes? You may not have. Okay, so if I'm moving, the Coriolis force pushes me in the northern hemisphere to the right of my motion. And there are a couple of different ways to understand that. One is to do what we're doing right here, which is we just write out what that cross product is, and then we think about which direction it's in. But some people like to think of this in a more heuristic way, like on the Earth. So here's my Earth. rotating around a vertical axis like this with speed omega. Okay. So which part of the Earth has the fastest tangential velocity in this solid rotation?
The equator.
Right at the equator. It's going the fastest around the middle. So the middle is going really, really fast. Up here, it's not going tangentially at all. It's just spinning around the vertical, right? So everywhere in between is going somewhere slower in terms of tangential velocity. Okay. So if I'm a parcel of fluid or a cannonball or whatever you want to think of at the equator, and I move north, or I try to move north, I can't just move straight north, or I'd have to exert a force to move straight north, because my angular momentum would be greater than my environment. Does that make sense to everybody? I could move directly north and go up in the sky, I guess. I could leave the Earth behind and continue. But when we stay on the surface of the Earth, we're reducing our distance from the rotation axis. And so we would have, and this one actually has a smaller velocity as well. Centrifugal acceleration is v squared over r. So if I go up here, the v has gotten smaller, because what's the v in a solid body of rotation? It would be just omega times r would be the velocity, r perpendicular from the rotation axis. So as I get closer and closer to the rotation axis, my velocity, tangential velocity, is getting smaller, and also the moment arm I had away is getting smaller. So in order to conserve my angular momentum, I would actually end up going something like that. Does that make sense to everybody? In our equations of motion, that effect is captured. That is what the Coriolis force does. It pushes us to the right in the northern hemisphere. If I were going the other way, I would find myself with a deficit of angular momentum. So I would also get deflected to the right. But it would be going the other way. Okay? Does everybody understand that part of it? Okay. What if I'm going east? This is the harder to think about one. So this one is easiest to think about the centrifugal force. If I'm going east faster than the planet, I would actually kind of experience like an excess of centrifugal force, or more precisely, my centrifugal force wouldn't be in balance for that motion. So I would get thrown a little bit outward from the rotation axis, which takes us south. If I were moving west, I can do the same argument in reverse, and that would push me north. So in every case, I get deflected to the right. In every case, the degree of deflection is proportional to my velocity. And now it is not at all obvious that the cross product like that is the right way to write this, but it is. Okay? So I claim that this little dynamics here are exact in case those four classes of motion. Okay? So if I am accelerating, if I have some v velocity, so v velocity we think of as this direction, and if that's positive, then this too will be positive, which is this guy. It will be accelerated in that direction. if I have some u velocity, this guy, then it would cause an acceleration of v towards the negative that way. And I can flip the signs and get this guy and that guy back. That's the same motion. Okay? Does everybody see how that fits together? Sort of? Okay. So now here's the bigger magic of this. Can you solve that set of equations? In general. So this is a what? Two coupled first order ordinary differential equations. They're ordinary because it's only time derivatives. So at every point in space, the spatial derivatives don't matter. We kind of threw them away by throwing away that term. So I could take the time derivative of this equation, and then I'd end up with a ddt of v, and then I could plug this in and put that in there and substitute in, and then I would get second time derivative of u minus 4 omega squared u. Or I could do it the other way and I get second time derivative of v equals minus 4 omega squared. What does that look like? Second time derivative of something plus a term that's proportional to the same something equals 0. It's exactly. It's either going to be an exponential or sines and cosines. And in fact, if you work out the sines, it's sines and cosines. So this means sines and cosines with the u, the initial u velocity on these two terms, and the initial v velocity on those two terms. To make it simple, we can just forget one of them and say it was initial all u, and then it's cosine and sine. So if something has cosine in the x direction and sine in the y direction, it means that it just does circles. It just loop-de-loops in little circles. So inertial oscillations are little loopy circles. And they have what period? The angular frequency is 2 omega. So 2 omega is the angular frequency, which is 2 pi over the period. And this is 4 pi over a day. Okay. So there's a factor of 2. There's a crazy missing factor of 2. Is a day over 2 is equal to the period. Yeah.
In real life, so what starts this is like perturbation of whatever current you're looking like Taylor-Proudman, for instance. In real life, is there something that makes it stop at some point?
So if these, so suppose like the upper layers of the ocean were oscillating like this, then they'd be dragging on the lower layers. So you might actually be, or if it was the whole ocean oscillating like this, it'd be dragging on the bottom. So there would be some frictional boundary layers that would tend to slow you down. So if you kick the ocean like this, it would all start jostling around twice per day, doing its thing, or twice per pendulum day, which we'll talk about in a second. But the bottom drag would eventually slow it down. So the fact that there's relatively little drag, that viscosity is relatively weak in the ocean, means that these ring like crazy. They're just always kind of binging, binging, and that tank experiment shows that it was binging. And so in the tank experiment, it's 4 pi per rotation period of the tank. So we should see, go back to our movie. Do I have the movie next one? You need to go faster in the movie. Okay, if we zoom in on one of these. Okay, one. So it should be wobbling twice. Its period should be half of a rotation period of the table. It should wobble back and forth twice as often as the table goes around. In which you can see, I mean, it's plausible that that's what it is. It's kind of hard to do it without a stopwatch to figure out exactly what it is. But that's the oscillation. And so we're only seeing one part of the circular motions that are going in here because the stripes are kind of removing part of it. But I would claim that all those motions are actually little circles, that we're just seeing little circles going like this. And so we see it when they go off kilter with each other. Yeah.
So you're saying that the period is the period of the wobble, not of like the period it would take for something to do a complete circle?
Yeah, so it's the period of the circle. Oh, wait, where did it go? It's the period. So for this guy to go all the way around, it's the period of this sine function. So, but that period is not the angular frequency of the Earth. It's twice the angular frequency. The frequency is twice as high, or the period is half as long. So the period is half of a pendulum day.
Are you saying the little eddies in the video rotate twice every cycle, or?
Yeah, so they're going around twice every cycle. So that, let me try and draw the rotating. So if the rotating tank, this is maybe the best diagram that I've figured out to keep track of what's going on. So in the frame of the lab, the rotating tank is going around and around. So we could think of a part of the fluid that's going around and around in the frame of the lab. So here's the center of the tank. That's just a part of the tank that's going around and around. So inertial oscillations are like this kind of a trajectory on it. So they are farther away from the center of the tank 2 times per day, and they are closer to the center of the tank 2 times per day, or 2 times per rotation. So now, this is the tricky part. What's that relative displacement? It's supposed to go, oh, now it's backwards. So if you draw the little arrows in, you can convince yourself that what that's doing is it's spinning around away from the circle, which is its undisplaced location, twice per day. Once it's displaced this way, once it's displaced this way, and it's displaced inward on those two. Does that make sense? Okay. So that's what this guy's telling us. Okay. On our famous F plane, our tangent plane, we don't get the full 2 omega. We get 2 omega times the sine of latitude. So the period is actually a day divided by twice the sine of the latitude. So sine of latitude at the pole would be twice per day. That's what we get. But at the equator, it's infinity. So it gets slower. The pendulum day is longer than the day the closer you go to the equator. So in practice, in mid-latitudes, this isn't 12 hours, it's more like 26, 30, whatever. So these oscillations have different periods depending on the latitude you're at. So it's twice per day, twice per pendulum day, twice per day at the poles, once per day at 30 north or 30 south, because that's where the sine of latitude is a half. So it cancels the 2. Does that make sense? All right. Okay. So do these things exist in the real world? Yes, they do. Here's an example of a drifter that was observed wobbling around. So there's a mean current, apparently, that's going like this, but there are little circles with deviations away from that mean, and each one of these slashes is 12 hours apart or something like that. So if you pay attention, you can figure out what the period was. And this is at 57 north. So it's not quite at the pole and not quite at 30 north, so it should be somewhat faster than twice. It should not be as fast as twice per day, but should be faster than once per day on the oscillation period. And depending on where you go, and here's a crazy one that if you go north of the equator and then south, you go in opposite directions, like a figure 8. That's a super crazy one. I don't know if that's ever been observed. But you can imagine loop-de-loops all over. They go the other direction in the southern hemisphere because F is negative down there. And you can think of it as a simple force balance that basically just the centripetal acceleration is always provided by the Coriolis force. That's the force diagram. Just inward the whole time. okay? And then these are power spectra from Wunsch of moorings in different locations. But this spike right at 01, which is the inertial period, I think, in this, is inertial oscillations. Just in every current you look at, it's just got inertial oscillations like crazy. That's 47% of the velocity variability is due to the inertial oscillations, or near inertial oscillations. 57% here, 18% there. So it's a huge signal. So when you go out in the ocean and you just measure something, the first thing you expect to see is this. And then everything else is kind of a deviation around that. That Taylor-Proudman part is sort of slowly underlying that motion. Why do I say that the Taylor-Proudman part is slowly underlying the motion? How do I know that the Taylor-Proudman part is slower than the inertial oscillations? The scaling, because in order to get to Taylor-Proudman, I said the temporal Rossby number was small. The temporal Rossby number for an inertial oscillation is equal to 1. The period is exactly so that the Coriolis term and the advection and the acceleration term are in balance. So those are the same size. So if the temporal Rossby number is small for the Taylor-Proudman, it means that the Taylor-Proudman flows are slower to accelerate because their acceleration term is negligible compared to their Coriolis term. So there's slow Taylor-Proudmans, and then there are inertial period inertial oscillations. When I go down here and I see things like the tides or these other waves that are there, what's their Rossby number? If the Rossby number is 1 here at the inertial oscillation, and slower things have Rossby numbers smaller than 1. Which way are slower things? If this is cycles per hour? This way. The low frequency end is over here. Slow stuff is over here. So all this is small Rossby number. This is Rossby number equals 1. What's this?
High Rossby number.
High Rossby number. So the effects of Coriolis force are greatest here. Relative effects greatest. Same as acceleration. Over here, acceleration dominates Coriolis. Okay? Yeah, I wanted to show you this cool thing, but I think I need to tell you something about Ekman first. Okay. All right, so we started out with this crazy thing I'm going to show you. So this is the balance for inertial oscillations. This term equals this term. And that happens when the advection is small. This is small. Rotation and time change are the same size. Friction and density, this stuff, small. So our advective Rossby number is small. Our temporal Rossby number is 1. And our Ekman number, which is going to measure friction, is also small. Okay? Hydrostatic balance is these guys. Turns out you can get that from just having small aspect ratios, so motion that's wider in the horizontal than the vertical. We didn't go through that carefully. The Taylor-Proudman theorem included these 3 terms: gravity, pressure gradient, and Coriolis together. So those are all the same size. It happens when you're rapidly rotating. So both the advective and temporal Rossby numbers are small. Those terms are negligible. The friction and density variations are neglected. And the rotation axis direction in one particular is the only thing that's constrained. So we're going to start thinking about these balances like this. What terms in the momentum equation are active? And what are the assumptions that we had to do to get there? Does that make sense to everybody? All right. So the last thing I want to talk about is the Ekman layer. Oh, well, I'll just run this thing. This is cool. All right, so there's a little code, and I actually give you the MATLAB code that you can go experiment with. And so this is supposed to make you start to understand a rotating frame and a non-rotating frame simultaneously with the same motion going on in both. So this is the rotating frame. So this is like the rotating tank. This is the inertial frame. And this is just showing an inertial oscillation. So here's the inertial oscillation going around and around in a circle. And it goes once. Second time around. And then when it completes the second time, that guy's gotten back to it. So it is really going around twice for the rotation of, and sorry, these axes are showing the axes in the other frame. So if you're in the rotating frame, those are the axes of the inertial frame. If you're in the inertial frame, those are the axes of the rotating frame. And this is the motion in the inertial frame. So it's this little ellipse that I just drew for you. So you can see when we're up, and we're going this way, then we're coming back down this way. Now we're going this way. And then we're going this way. So you can start tracking these things. And then this is showing you the velocities, the x positions and the y positions in the different frames. So you can start to look at that sine, cosine, and start thinking about how that fits together. You can also do crazy things like turn off the centrifugal force and just see what happens. There's lots of fun to play with. Okay? So the link to that is in the slides and it's on my webpage. That's just a little MATLAB code that has a how-to direction and things. We'll probably show that one more next time. Okay, but let's look for a moment before, here's me again. I know, I get strained, you know. It's a lot of zooming in. These moments in the videos are always very awkward. I have cut a few, I have actually edited it a few times to do that. Okay, so we're going to talk a little more about inertial oscillations with the Ekman layer. The Collins, the ocean circulation book, really has a nice discussion of all of these effects, and just with mostly words, with just a few equations. So it's a, well, and lots of the figures I'm showing are from that. So it'll help ground it to start looking through that. Okay, so here we go. Hydrostatic balance, Taylor-Proudman, Ekman layer. Okay, what's Ekman layer balance? Which terms are active? Okay, is it small Rossby number or large Rossby number? Small, because we're keeping the terms in blue and getting rid of the white ones. So this guy being smaller than that guy is small effective. This guy being smaller than that guy is small temporal Rossby number. We're not going to worry about these for now. So there's not, there is a dimensionless quantity, we will worry about that, but we're really going to say is friction is going to be big. Friction is going to be important. So the two biggest terms are going to be Coriolis and friction. So it's going to be rapidly rotating, and it's going to have important friction. The Ekman number is the measure of friction, and so it's got the viscosity in it. It's got a Coriolis, and it's got a length scale squared because of this. So the Ekman number is telling you about the ratio of this term to this term. And when it's order 1, it means those two are the same size. Okay? All right, back to Taylor-Proudman. Okay, this isn't probably enough for us to talk about today, and then we'll quit. Okay, so the Ekman layer which direction, so this Laplacian, right? So what's the Laplacian? It's ddx squared plus ddy squared plus ddz squared. Which direction in the ocean is going to have big change over short distances? The north-south direction, the east-west direction, or the vertical direction? Vertical because of stratification, and also vertical because the ocean is really, really thin. Remember, the ocean's like the paint on a globe. It's 10,000 kilometers wide, 4 kilometers deep. So we expect the vertical gradients to actually be pretty big, and even bigger than that because of the stratification. So I put a little h here in the Ekman number to signify that we're really paying attention to the vertical distances when we're scaling this term. And so we're really going to pay attention to a balance of vertical derivatives of velocity versus the Coriolis force. Okay? And what's interesting about that is, okay, if the viscosity is really small, and Coriolis is whatever it is there some h for which the Ekman number is always 1? So suppose I tell you that the viscosity over friction is 1 in some units. Then the Ekman number would be 1 if h was 1. Okay? Everybody's on board with that. What if the viscosity is really small? So viscosity over F is, say, 10 to the minus 2, which is actually not so far about from what it is in a liquid, in water. H just needs to be small. If it's 10 to the minus 1, 10 to the minus 1 squared, would say that. So that says centimeters, 10 centimeter scale, this is order 1. If the viscosity was bigger, I would just look at a deeper layer. So it doesn't, whenever no matter how small the friction is, there's always a layer small enough that this term becomes important. And so in the real world, with this being a turbulent viscosity, which we don't have time to talk about today, but which we will talk about next time, this layer is going to be order of kind of meters to maybe 100 meters. So we can visualize it as being a little range at the surface or at the bottom of the ocean where friction is important. So there's a frictional layer at the top, there's a frictional layer at the bottom. That's the Ekman layer. That's what we're thinking about. And at the surface, the friction is really going to be generated by winds kind of dragging along the surface and trying to push the water that way. But it's not going to be as easy of a response as that, because when we push the water that way, which way does the Coriolis force go? That way. So then it starts spinning around in inertial oscillations until it's very unhappy, until you get to the point where the Coriolis force is opposing the force of the wind. And then you could happily be in balance. So we turn on the wind, we let the inertial oscillations do our thing and die out. And we'll come into balance with the wind, balance with the Coriolis force. Does that make sense to everybody? Which direction does the current go if the Coriolis force goes this way? In between. Okay. So the Coriolis force is to the right of the direction of motion. And therefore, if the wind is opposing the Coriolis force, the direction of motion has to be to the right of the wind. So the wind blows this way, it does some stuff, it settles down, and it settles down going that way, not in the direction of the wind. So I know that's totally weird, but that's what the Ekman balance is. Does everybody have a sense of how that works? We're going to keep talking about this next time, but I want to give you enough ingredients to do it. So we can go through our same game of scaling the momentum equation and come out with these terms, where we have basically we're just keeping the Coriolis term, keeping the friction term. That's the whole game. And we'll go through this again next time, but I just wanted to give you that. Now we're going to do this complication. All right. So how big is the viscosity in water? There's two ways to think of it. One is that water has molecules in it, and the molecules mix up momentum. So viscosity from that is relatively weak. But frequently, we pretend like turbulent mixing in the ocean of big eddies behaves the same as those little molecules. So if a molecule is going fast at the top and then it dives into the lower, it'll deliver some momentum. Or if it's moving slow in the bottom and then it comes up, it'll decrease the momentum. So that's what normal viscosity does. In the same way, if you have an eddy that's moving fast in the top and then it dives into the lower, it's going to slow down it's going to speed up the lower layer. If you have one that's going slow, it'll slow down the upper layer. So in some very rough sense, we can pretend that turbulence is a like of an additional viscosity. The viscosity is bigger because these bigger eddies are more capable than molecules at carrying momentum back and forth. So that's the idea of an eddy viscosity. And we'll come back to that in the end. But the amazing thing, so this is Ekman. The amazing thing is once you have made that assumption, you can actually solve the equations all the way through for the viscous layer that responds to stress at the surface from the wind and no motion at depth. It's this complicated thing, but we can look at a figure of it, and it looks like this. There's a spiral on the way down, and the net transport is perpendicular to the direction of the wind. Okay? So, we're going to stop here. No, oh, wait, we're going to stop here. So, what's different about this and that? It's a mirror image. And so, why do I put the mirror image on? Because it's the southern hemisphere that's the mirror image of the northern hemisphere. So in one direction, the Ekman spirals to the left in the southern hemisphere, and it spirals to the right in the northern hemisphere. And that's implicit in these solutions because they depend on the sign of F. So if F is negative, it just goes the other way. Okay? All right. So we're going to keep talking about Ekman next time, and we're going to come up with this important formula. This is going to be the key formula, which is already in Calling. This is the only formula I think you need for the homework, is to think about this one and maybe the next one. It's discussed in Calling, but you can start looking at the homework already from this. All right? Okay. There's a lot more to say about Ekman, and I realize there's a lot of things moving all at once. These are complicated ideas, but they build on top of each other. So we'll keep talking about scale analysis. We'll keep talking about Coriolis force until it starts to seem really obvious. But today was a big blast of new stuff. So Tuesday we'll come back to a lot of the same ideas and just keep building on them. And then eventually it'll start to make sense and you'll start to see how the equations fit together. That's the target. Okay?